Hello. We are going to present a paper accepted for the software engineering, quantum software engineering workshop entitled Quantum Software Models, the Density Matrix for Classical and Quantum Software Systems Design by Yaakov Exman and Alon Tsalik-Shmilovich. We have two main messages. The first one, single rigorous design procedure for both classical and quantum software. The second one, common starting point, von Neumann's density matrix. Our agenda starts by introducing the Laplacian matrix. Then we describe our theory, including density matrix, software modules, theorems and procedure, case studies, classical, referring to the prototype design pattern, quantum, referring to Grover search algorithm, and we conclude with a discussion. The Laplacian matrix for software systems is based upon a bipartite graph. The bipartite graph is a description of the software systems. It includes structures, which are a generalization of classes in object-oriented design, for instance, S1 to S4, and functionals, which are a generalization of class methods from F1 to F4. The formal definition of a Laplacian matrix is L equals D minus A, where D is the degree matrix, which is a diagonal matrix, seen here on pink background, displaying the degrees for each of the vertices of the bipartite graph. And A is the adjacency matrix, showing the neighbors for each of the vertices in the matrix. For instance, S2, the structure S2 has two neighbors, F1 and F2 functionals, and it is, the meaning is that S2 provides the F1 and F2, and so they are linked. How to get modules from the Laplacian? Very simple. One calculates the eigenvectors of the matrix. And for instance, here we have for the previous matrix, 3 eigenvectors with the respective vertices on yellow. The first eigenvector has indices 1 showing F1, F2, S1, and S2 as labels of this 2x2 module. The next eigenvectors are 1x1 modules, F3 and S3, F4 and S4.
The density matrix enables both classical and quantum software systems. Density matrix ρ is actually a matrix representation of a density operator, which is a projector, and we'll discuss it later. It is notated as ket bra in Dirac notation. As you can see, that ρ equals ket of psi and bra of psi, where psi is a generic notation for a quantum state. Density matrix ρ is obtainable from the Laplacian. You can see that ρ equals the Laplacian divided by d of g, where d of g is the sum of the degrees of the graph G. Density matrix provides novel perspective on software modules. It's actually a sum of projectors of Kat's basis set. In the Laplacian we saw earlier, its size was 8 of 8. Therefore, we use the Kat's basis set 0 to 7. The definition of module of software system is subsystem spanning a subspace of the whole software system. We use two theorems in our procedure. The first one is number of software modules. These are the numbers of partition classes of projectors. And the second theorem is components of software modules. These are destructors and functionals fitting the projectors of partition classes. The procedure to obtain modules is as follows. First, we apply density matrix to each cat obtained projectors. And then we partition the projectors. We define the number of modules, and the components of each module is given by a basis cats of the respective projectors.
We now present two case studies. The classical one about the prototype design pattern. The structures and functionals are obtained from a class diagram of this system. The structures are a generic clonable shape, a specific shape like triangle, square, circle, losange, cache to store shapes, and a client to trigger the whole calculation. The respective functionals are a clone and the calculation of a specific shape, such as a perimeter or a surface of the triangle. If there are already shapes in the cache, one can retrieve the desired shape. If not, one clones the shape and stores the shape in the cache for further use. The main is the function inside the client. The respective density matrix is as follows. The Laplacian is recognizable here. And before the Laplacian, one see that one multiplies by 1 over 10, where 10 is the sum of the degrees in the diagonal. And another point that we want to emphasize is what are the meanings of the cats above the columns and the bras to the left of the rows. For instance, if we apply the density matrix on the cat 101, we obtain the column S2 with the respective coefficients -1, -1, and 2. The projectors can be obtained from the respective cats and bras. And here one can see immediately that the projectors upon the yellow color and the orange color and that in the green column, they are disjoint. For instance, the cat 100 is not found in the orange set and not in the green set. So these are 3 disjoint sets of projectors, and according to the theorems that we mentioned before, these divide the system into the modules. So the yellow one is a 2x2 module with the labels F1, F2, S1, S2. Then the 2 others are the F3, S3, and F4, S4. How to validate these modules? Very simple. One just compare with the linear software modules Laplacian eigenvectors in slide 5, and one can see that the modules are exactly the same. The quantum case study is about a well-known Grover search algorithm. The quantum circuit for this algorithm is seen here. It has 4 boxes, each one containing the respective operator. For instance, the initiation contains the Hadamard to the power of tensor n, which takes the input into an equal superposition state. The oracle recognizes and marks the target. The target amplification causes exactly the expected amplification by inversion about the average. This is an expression of the functional, and the purpose is as follows. This marked target has an amplitude that in each cycle is going up and up and up until it is almost the only item that has almost 100% probability of being caught by the measurement. The two structures, oracle and amplification, are together the Grover iteration. They are marked here by the light blue, meaning that after the initialization, which is done only once, and before the measurement, which is done only once, there are a few cycles of the Grover iteration in order to amplify the desired target. And the number of cycles is of the order of square root of n, the number of items being searched. How we obtain the structures and functionals in a complete analogy to the classical case in which we obtain the information from the class diagram. Here we obtain the information from the quantum circuit. The boxes, the green boxes are the structures, and the gates inside the boxes are the functionals. The structures were described previously, and the same about the functionals. The only point that we wish to stress again here is that the oracle and the amplification together constitute the Grover iteration. And so this is a module, the 2x2 module in this case. The oracle expression is I minus I is the identity operator, minus 2 twice the projector, the Cat-Brown omega, the marked target. And the amplification is 2 times the Cat-Brown psi. Psi are all the elements being searched, minus I. One can see 2 things. First, the functionality of both oracle and amplification are exactly the same, except for the argument omega and psi. And another point that the amplification is the oracle multiplied by minus 1. This identical functionality is again similar to the classical cases of the software systems, in which within modules one has inheritance. So these functions are the same except for the argument in the minus 1, which is an additional functional needed to invert about the average. The density matrix is seen here. One can immediately pay attention that it is very similar to the prototype design pattern, the classical example that we gave. Is this expected? So why should so different systems such as the Grover search algorithm and the prototype design pattern have so similar density matrices? It is rather by chance, it is not expected, but there is one point that is very satisfactory for us, that the quantum case and the classical case are very similar, implying that it is very reasonable to apply the same design approach to the quantum and classical cases. One point which is obviously different is that the 2x2 module here is located in between the 1x1 modules, whereas in the classical case, it was in the top location. Discussion. First point, a different density matrix of a software system may serve for distinct purposes. And second point, classical software systems are classical limits of quantum systems as expected in physics. Moreover, there are striking similarity between the density matrix and software system. The density matrix is both a state of the quantum system and an operator applicable to states, while the software system, again, is both a state in the sense of the readable code, and it is an operator runnable upon states, which are the inputs to the code. We conclude by repeating our two main messages: a single design procedure for classical and quantum software systems, and a common starting point, the von Neumann's density matrix. Thank you very much for your attention.